In this video, I would like to give you a talk about our paper entitled, Masksembles for Uncertainty Estimation. Uncertainty estimation is one of the most important and developed areas in classical machine learning. On the other hand, often that's hard or even impossible to successfully apply these existing approaches to deep learning models. At the same time, a great number of modern applications require uncertainty, for example, medical applications, finance, self-driving, robotics and reinforcement learning, active and self-supervised learning. Bayesian techniques are one of the most popular approaches to uncertainty, for example, Markov chain Monte Carlo and variational inference. They have solid theoretical grounding, but at the same time often they could be slow, hard to train, and show worse uncertainty quality. One of the most popular approximate Bayesian techniques for neural networks is MC-Dropout. The general idea of this approach is to generate random binary masks during inference and zero out some of the network's activations. It is extremely easy to use, but it suffers from drawbacks discussed earlier. On the other hand, ensembling approaches demonstrated great ability to generate high-quality uncertainty, but they require high memory and computations overheads, in addition to increased training time. That makes ensembles unsuitable for many memory-constrained applications. The idea of masksembles arises from the following observation: both MC-Dropout and Deep Ensembles approaches could be represented as inference of a set of models. In the case of Deep Ensembles, these models don't share common weights, whereas in MC-Dropout they share a major fraction of them. This way both of them could be described as masking procedures. More concretely, Deep Ensembles is a masking model with masks that don't share any features and have a finite number of masks, whereas MC-Dropout has an infinite or exponentially large number of masks, and during inference it samples some of them. Varying some of the parameters of such models allows us to create a transition between mentioned models. The general idea of masksembles consists of two steps. The first step is to pre-generate a set of binary masks with required properties. The second step is to train our model with these masks in MC-Dropout fashion, by multiplying network activations with sampled masks during training. As it was discussed before, one of the properties of masks is how many features they share. We measure the correlation of masksemble submodels as an average intersection over union of generated masks. 0 means masks don't share features at all, 1 that they share all of the features. The second important parameter of generated masks is the actual number of generated masks. We argue that in the limit masksembles model starts to behave similarly to MC-Dropout model, including longer training time and decreased uncertainty quality. We compared masksembles model to both Deep Ensembles and MC-Dropout approaches in terms of behavior against common corruptions, both for CIFAR and ImageNet datasets in terms of calibration and out-of-distribution detection tasks. Our experiments showed that masksembles able to generate uncertainty of good quality, which is comparable to ensembles 1. The major takeaways from our work are: masksembles is a cheap and easy to implement approach to uncertainty, and it's possible to use it with literally any architecture. It allows spanning the whole space between ensembles and MC-Dropout and taking advantage of both. Proper tuning of parameters allows making use of computation/quality trade-off. Thank you for your attention. For further information, please refer to our projects page.